An on-chip current source design is presented in this example. The circuit is implemented with a number of bipolar junction transistors. On top, we have 3 matched PNP BJTs, and at the bottom of this circuit, we have a number of matched NPN bipolar junction transistors. There are 2 supply voltages shown, V positive and V negative, even though the circuit can operate with single supply. We would like to see how this circuit is working and why it's a suitable design for, or suitable choice for on-chip circuit design, especially let's say when we are designing operational amplifiers on-chip that require a current source. And also we would like to find the value of this I/O at the output of the circuit. I would like to show that this I/O in this design will be independent from the value of supply voltages as long as we have minimum supply voltage required. That's a very interesting property. And then I would like to show the voltage compliance range, which means what is the min and max voltage values at the output of the circuit that would be acceptable. So upper and lower threshold for the output voltage. What is that? Which we refer to as voltage compliance. This is mostly an on-chip design, but if we were curious to implement this using discrete components, then here are potential choices. There are many. For example, MAT14 is a packaged matched monolithic quad NPN transistor from Analog Devices. So there are 4 matched NPN transistors, bipolar junction transistors inside this package. If we want PNP ones, then Fairchild has, for example, this solution, these part numbers that are basically multiple choices for either quad package PNP or dual package PNP or quad package PNP, in which there are 4 inside, 4 PNP transistors. So discrete components are available that are meshed as well. But on-chip design has the benefit that we can have these transistors very close to each other and sort of copy paste on the same substrate so that we make sure they benefit from the same junction and thermal properties. So PNP transistors should be copy paste, and NPN transistors should be matched as well, except that for this one shown here we will need to have scaled up emitter area so that while the current density is the same for these NPN transistors, we benefit from increased current for this one. I'll talk about this one later. So to start analysis, let's focus on these PNP transistors. What we have, we can use and write the Shockley equation for PN junction. So we know that the famous Shockley PN junction IV current voltage equation is basically saying the voltage of a base emitter or emitter base, doesn't matter, basically the voltage of PN junction. In the case of the PNP BJT transistor, we are dealing with emitter to base, which nominal is 0.7, but the accurate formula is VEB equal to ideality factor eta. VT is the thermal voltage, which is KT over Q. K is Boltzmann constant, T is the junction temperature in Kelvin, and then Q is the electron charge. We know K over Q is just roughly on the order of 86 microvolt per degree C. So, and then we have natural log of the current of collector divided by the saturation current of the transistor. So we know this. I'm going to use this, and in the process we are making the assumption that these are silicon, let's say bipolar junction transistors. So we are dealing with silicon PN junction, in which eta, or ideality factor, which is a value between 2 and 1, can be assumed to be close to 1. So I'm going to neglect eta in the computation that we have here. So VEB is approximately thermal voltage natural log current of the collector divided by saturation current of the transistor. So that is what we're going to use. In the process, when we have KT over Q for the room temperature at roughly 290 degree Kelvin, which is roughly on the order of, so let's say room temperature, let me put it this way. So VT at room temperature, which is on the order of 17 degrees C, 17 to 20 degrees C, let's say, is basically in Kelvin would be on the order of 290 Kelvin. So if we compute VT, we end up with something on the order of 25, roughly, millivolt nominal at room temperature. Okay, so with that in mind, let's proceed. Just we need to bear in mind that this emitter base voltage of the PN junction of the PNP transistor is heavily temperature dependent, linearly via VT, because VT is KT over Q. You can see that there is a linear dependency on temperature, and IS is exponentially dependent on temperature, so we want to get rid of this IS. So what happens is, since these two transistors are matched basically, or these three transistors are matched, then because the value of R and R is also matched, they are the same resistor value, therefore we can make the assumption that the current that is going through this one, which is I out, is the same as the current that is going through this one, which is, let's say, I3, if I name these transistors as T1, T2, T3, T4, T5, and T6, that I'm going to talk about this transistor later. Okay, so with that in mind, I'm going to write this equation. So I'm going to write I out should be equal to I3. That's equation 1, as long as these transistors are matched and these resistors are matched. So we have that property. Now, let's focus on the combination of T2 and T3 for basically I2 and I3. So what I can write is, I can write a KVL by saying that the voltage drop across the supply rail and the base for transistor T3 is the same as voltage drop between the supply rail and the base of transistor T2. So basically KVL, or Kirchhoff voltage law, in the sense of these two parallel voltages should be the same. I can say I3 times R, which is the voltage drop across R, should be plus the V emitter base of transistor T3 should be equal to basically just emitter base voltage drop across transistor T2. So V emitter base of transistor T2. Now I am going to use, let's say this is equation 2. I'm going to use equation 2, which is the Shockley-PN junction IV equation. So, and I'm going to substitute for VEB3 and VEB2 using the equation that I have. So I3, and by the way, maybe I can do it later. I can substitute I3 with I out using equation 1, but I'm keeping it for later. So I3R is equal to, I can move this to the other side, so I have VT natural log for VEB2. I can write, so that is this voltage drop, I can write I2 over IS, and for minus VEB3 I can write I3, this current, divide by IS. And since these are matched transistors, matched PNP transistors, therefore IS is assumed to be the same for them. That's the super important part, because now with this we can get rid of the IS. So what I'm going to get is, I3, and then at the same time I'm going to use equation 1 so that I can substitute for I3 and just write I out. So I am going to write I out instead of I3 times R is equal to VT, which is the thermal voltage, natural log of I2 over I3. Okay, that's interesting. So I basically managed to find that I out is equal to Vt over R natural log I2 over I3. So what else I can do about this? Well, in this branch, since these are very low current transistors, they have large beta. So beta, or the current gain of transistors, IC over IB, which is the I collector over I base, is assumed to be much larger than 1. They can be easily on the order of 200 to 500. I mean the beta values for these transistors. So with that in mind, we can basically just say the collector current is the same as emitter current and neglect the base current. So we can say I2 keeps going down through these transistors. So about this transistor T6, it's basically a scaled up emitter area. So what happens is, for instance, the emitter area on silicon or on substrate for T6, if it is, for instance, 3 times the emitter area for T5, then naturally when the voltage of base emitter drop is the same for these two transistors, but then we get 3 times, let's say with the 3 times area for emitter, we get 3 times current out of T6. So, but what I can do is I can write another KVL between the base of transistor 6 and negative supply. So that's 1 voltage drop, and I can set it equal to the voltage drop between the base of transistor T5 and the negative supply as well. So I can write voltage of base emitter of transistor 6 plus Rx times the current I2 that keeps going through this ladder, or let's say this branch. So Rx times I2 equal to, and for this one here I can write voltage of base emitter of transistor 5 plus Ry times the current I3 that keeps going on through this branch. But as I said, since T6 and T5 are matched NPN BJT transistors on the same substrate, they should have the same, let's say, base emitter voltage VBE. So that's important. So we can basically get rid of these two guys, and we can write Rx I2 is equal to Ry I3. As a result, I can say I2 over I3 is equal to Ry over Rx. Let's refer to this as equation number 3. So I'm going to substitute in this prior calculation from equation number 3, I'm going to substitute for I2 over I3. So what I get is I out is equal to thermal voltage Vt divided by resistor R natural log of, instead of I2 over I3, I'm going to substitute I2 over I3 by R1 over Rx. So Ry over Rx. This is the very interesting outcome we were looking for, because basically what this is confirming is we are able to find the output current of this current source as a function of thermal voltage, which linearly depends on temperature, then also choice for resistor R, which is the resistor R we have on top, the two matched resistors, and then Ry and Rx at the bottom of the circuit. So with that in mind, for example, if we want I2 to be, let's say, 3 times I3, then we need 3 times emitter area. So let's say, let me put it this way. If in equation 3 we want I2 to be 3 times I3 as an example, or let's say generally speaking n times, then that means Ry should be n times Rx, if that is what we desire. So obviously that means if the I2 is n times I3, since the base emitter voltage drop across these two transistors is the same, then KVL requires that the voltage drop across Rx and Ry should be the same, and therefore to counteract the I2 that is n times I3, then Ry should be n times Rx naturally, which is what this thing is saying. So let's say as an example, let's say in an on-chip design we are interested, just as an example, to have the output current source nominal for this circuit to be 100 microamp. I mean, in real chip design this can be as low as 1 microamp. So I'm just dropping a number here. It doesn't mean it's a suitable number. So let's say we like to have 100 microamp. Then in the at room temperature, as I said, VT is about 25 millivolts. So in this scenario I'm going to use result from equation 4, which is the formula for the value of the current source. So I out is 0.1 milliamp in this hypothetical example. VT is 25 at room temperature, let's say junction at room temperature, so it's a temperature of junction. 25 millivolt divided by R. I don't know what R is. Let's say the ratio of Ry and over Rxn is basically, just as an example, is just 5. So that is n equal to 5, which means the area for the emitter of T6 is 5 times the area of emitter T5, as if we have 6 transistor. Sorry, as if we have 5 transistor in T6, 5 of T5 in T6, as if. So with that in mind, we can find R, and R will turn out to be, just as an example, R will turn out to be this value. So let me just do a quick calculation here. It's going to be 250 and then times, so let me do it this way, 5, so ln5 is 1.61 roughly, and then times 250 will give us about 400 ohm roughly. So 402, I guess, 402 roughly ohm. So that's interesting. Basically, roughly on the order of 400 ohm resistor we need in order to get to output current source nominal fix at the 100 microamp in the hypothetical example that is presented here. Now that we know the formula for the output current, the next question, and the fact that the formula clearly indicates that the value of the current is independent of the value of supply voltage, V positive and V negative. You don't see any appearance of V positive or V negative in this formula number 4, as long as they have the valid values. So interesting property of this circuit is, if you take a look at extreme situation, which is not recommended, I'm just saying super extreme scenario, the lowest voltage drop across as the lowest supply delta, so delta V, that we need across this circuit in extreme scenario would be one transistor as a diode here, and another transistor as diode here. So basically this is a PNP diode and this is an NPN diode. So for them we need about let's say 0.7, and we need about 0.7 drop across these guys. And in extreme scenario, if this transistor is pushed to the limit, the minimum VCE, so VCE absolute minimum that is needed here is roughly on the order of 0.2, but not recommended to be pushed to this level. So it's as if we have 0.7, 0.2, 0.7. So the minimum absolute that is needed for this circuit in terms of delta supply is 1.6 volt. So this is delta V basically should be greater than 1.6 volt and preferred at least, let's say, 2 volt. So that's the minimum. As long as the delta between V positive and V negative is greater than 1.6, preferably greater than 2, then the circuit is functional and the output current is going to be governed by this formula independent of the supply voltage. Now, regarding the voltage compliance range, which means the upper and lower threshold of the voltage here, output voltage. So you can see that if, for instance, V positive or the positive supply is, let's say, 10 volt as an example. Of course, on-chip design, it doesn't go to this voltage. Usually for low power on-chip design, you're talking about plus minus 1 volt or plus minus few volt at most. But let's say if it is 10 volt, then what we have for the output voltage or V out, we can obviously say, for instance, we can say V out is equal to V positive minus, as you can see, we have Ri out drop across the resistor, which I'm trying to say is negligible, and then voltage of emitter collector for T1. So is minus Ri out, that's the Ri drop across the resistor, minus V emitter collector for PNP transistor 1. Okay, this is, in this example, is 400 ohm roughly. There you go. And the current is on the order of 0.1 milliamp. So we can neglect this. This is on the order, the Ri out is on the order of 40 millivolt. So V plus is 10 volt, for instance, and VCE1, if you're pushing to limit by increasing the output voltage to the extreme, the worst scenario is when this transistor is getting into saturation almost. So we need a plus minus 0.2 volt across the emitter collector in the worst case scenario, which is not recommended. So with that in mind, therefore we can say therefore we can say, sorry, I'm just trying to clean up. Okay, so with that said, we can say that this is equal roughly to just 10 volt minus, let's say, 0.04 if we want to be extremely accurate, minus 0.2. So you're talking about roughly on the order of 9.76. So that's the V out, let's say, max or upper threshold, pushing to the limit, not recommended to get to this level. And V out min is, of course, how far we can push this voltage V out at the output of the circuit, how far we can push it low before we break down the transistor T1, because this transistor at some point when VEC is greater than some value will break. So breakdown voltage happens. So I would say in that scenario we can say V plus minus Ri out minus VEC, let's say breakdown, or sometimes we just say minus breakdown voltage of transistor collector emitter of transistor T1, emitter collector of transistor T1. If this is roughly 50 volt, for instance, and this is negligible completely, and this is 10 volt for the positive voltage, then this is roughly 10 minus 50, roughly minus 40 volt. Again, these are extreme levels, so not recommended to get to these levels. Basically, we found the delta V that should be greater than 1.6, absolute lowest is 1.6, not recommended, and the maximum and minimum threshold or upper or lower threshold for the output voltage are also found in this design as the compliance range, though it's not recommended to get to these levels. I hope that I hope that this example is helpful, but basically in summary, the fact that we can realize output current on the order of, say, 110, 100 microamp in this circuit with reasonable value of resistors. Is not as if we need humongous or weird value of resistors. With reasonable realizable value of resistors, we can get to the target current in this design, which is a low power, low footprint design. And also the fact that the output current for a wide range of supply voltage So delta V just need to be greater than 1.6, and we have a very good compliance output voltage range. So given all these interesting properties, this is a very suitable and good design or topology for on-chip current source design, for which we really like independence from the supply voltage and a wide range of operation which this circuit provides. I hope this example is helpful. Thanks for watching.